Oh my God. Anyway, that's the last step, no, in the oxymercuration process. You simply have to remember that you have 4 steps in the oxymercuration. This is simply oxymercuration. Your end product is mercury acetate, hydroxyalkyl mercury compound here. To eliminate this one, you still need to have deoxymercuration. I will have to add demercuration here. Okay, you have to add your demercuration here. Step 5 for demercuration should be this one. In the presence of sodium borohydride and OH. Okay, and you will get, let's just start it. To get your select you'll get your OH. Okay, and of course what is eliminated here is you have your BH3. Anyway, you will eliminate that one, and your source, sorry, wrong. This one is your source of your hydride. So this is not OH but hydrogen. Okay, so you get your CH3, get your final product. That should be your step 5. If you want to eliminate your mercury here, you have to add your other agent, sodium borohydride. Okay, so that ends our discussion. It should be this one here. So calculations indicate that mercury-bridge carboxyl ions, such as those formed this reaction, retain much of the positive charge in the mercury moiety. Only a small portion of the positive charge resides on the Mars substituted carbon atom, and the charge is large enough to account for the observed mechanical addition, but it is too small to allow usual rapid carbon skeleton arrangement. So there is no skeleton arrangements, not the usual one that happens in the oxymercuration process. Although attack by water in the bridge mercurium ion leads to anti-addition of the hydroxy and mercury reaction, that this one is the anti-addition. Here, you have this one. If you have your mercury here, acetate in step 3, since here it's like a 3 ring, it's a bridge, no? So you will attack, your water will attack on the other side. That's why it's anti-addition here. You have your OH here, on this side, and your mercury is on this side, and later when you remove this demercurized your product, no, to have your hydrogen here, they are untied to each other. So here, the attack here leads to the anti-addition of the hydroxy and mercury groups. And of course, later it's an the net results of the oxymercuration is a mixture of syn and anti-addition of hydrogen and OH. So despite of that, you get a mixture of syn and anti here. And as already noted, oxymercuration takes place in mechanical bridges and activity. Okay, that ends our discussion for today. Do you have questions? If you have questions regarding your problem set last time, we can talk about it now if you are fine with it. Okay, Ramo. Who wants to discuss katong last time? Do you want to discuss or anyone? Would you like to discuss, or it's already time? Maybe on our laboratory time. Tomorrow we have our activity at sa university. So anyway, I'm just gonna leave you again. Hopefully another activity tomorrow. Do you have questions? Would you like to discuss our problem set katong inyong gipangutana no last time, which is itong problem? Problem set number 3, I think. Na ito lolag ako. 6.49. Maybe we can discuss that now. $6.49. Napay wala nakakuan. If napay tulo wala day naka-submit, no? Are they still planning to submit? If not, we will discuss. Pero if they are still planning to submit, maybe we will wait for them. Na itulo wala nakasubmit. I don't know who are they. So we'll wait na lang for them, or we can discuss that. Kinsay wala ka submit?
Wala po may kabalo.
So if mag-discuss ta karon the problem set, I will close that one. 16:30. Okay, so we'll discuss that and I will close first the problem. No one should be piyasa na ganito. We have the problem. I will share na lang. Stop. Share. Okay, so problem 6.49, I think this is the one that you had most difficulty answering. When S2 bromopropanoic acid, SCH3, then reacts with concentrated sodium hydroxide. No, the product formed after acidification is R-hydroxy propanoic acid. First and foremost, we have to write on the structure of this CH3 CHBr. Okay, so you have your S here, and you have to write in such a way that it's an S form. No, then the product is R lactic acid. This is of course the normal stereochemical result. So there is an inversion of stereochemistry, no, from S to R. When you have your sodium hydroxide added here, so your Br is the leaving group, and you have your OH added, you have your CH3 CHOH, so the Br is replaced with OH, you form your lactic acid here. This is of course the normal result of the stereochemical reaction. Stereochemical result for an SN2 reaction. However, when the same reaction is carried out with a low concentration of the hydroxide ion in the presence of Ag2, Ag plus, no? So Ag plus acts as a Lewis acid. What happens is take place with an overall retention of configuration. So instead of R, tama ba? So you have your 2-hydroxypropanoic acid, this one. So 2-hydroxypropanoic acid. But this is not the lactic acid, no, because the lactic acid is in the R form. But this is the enantiomer of the lactic acid, 2-hydroxypropanoic acid, 2. And so write a detailed mechanism for this reaction that accounts for the result of the configuration when Ag plus and a low concentration of the hydroxide. Okay, so you have your Hg plus. Now the Hg plus is a positive. It acts as an catalyst. It acts as a catalyst here. Here you don't have a catalyst, you don't have your Hg. If you have a general reaction, print screen, you have a general reaction, you have your hydroxide, and the condition for your SN2 reaction, no, it's a concentrated sodium hydroxide. You have an NS2 reaction, and you have a 2-degree alkyl halide here. So still it can follow the SN2 reaction, the tertiary fats or for the SN2. And you have an inversion of configuration when you have your SN2 reaction. Always remember that. But in the presence, when you have a catalyst like Ag silver oxide, no, and you get your Ag plus, can act as a Lewis acid here. There is a retention of configuration going on. So we provide a mechanism for how this one happens. Okay, so let's have that one. Okay, you have to remember that Ag plus, no, is okay, share. Ag plus, it's passively charged, no, and you have to look for an electrons for an atom which is electron rich, no, for then it can. Okay, so here you have your two. Okay. You have your S-bromopropanoic acid, tama ba niya siya? Paste. So 1, 2, 3, propanoic acid in solution. Your propanoic acid dissociate to form your ions, your carboxylate ions here. Okay, so you have your Ag2. Your agent is Ag2. Okay, Ag2O. And this one actually can form your Ag plus. Okay, so you can dissociate to form your Ag plus. No? So it will dissociate one of the O will react with water no, to form your hydroxide. You get your Ag plus. Okay. So once your Ag plus, you get your Ag plus. What happens that you look for the system here in your S2 bromopropanoic acid. You have 1, 2, 3, 1, 2, 2 bromo. You have your bromine CH3. Which electrons or which atoms here will be electron rich no, or electronegative or would have an electron density that can donate electrons to your Ag. Now, this is our Lewis acid. You have to remember this is our Lewis acid. There is always a space where it can accept an electron. So there's 3 possibilities where you can have that one. First one is you have your OO here. But since you have your double bond here, they actually form electron delocalization in the acetate. Now, you will have your double bond running towards C, this first oxygen here, C double bond O. At that instant, you have C O bond here. This becomes the negatively charged, and this will become the negatively charged at times. So you have -1/2 hybrid throughout this oxygen here. Okay, so it's not the electrons in here because it undergoes electron delocalization, pi electron delocalization. It's not available to donate so much to your Ag here. So one atom that is very highly polarizable where it contains an electrons. Okay, that declare akong that there is contains an electrons, right? So 6 kabuo. And so it can form a bond, a partial bond with Ag. It can share its bond to Ag. Okay, to have that. So it can share with Ag, and your carbon then will become partially positive here. And to eliminate the partial positive charge from carbon, what happens is the oxygen, which is adjacent here, will form a bond here. Okay, this is partially negative. Sige, pakutangan natin ni siya og negative, partial negative, para makita ninyo, no? So this becomes partially, okay, it's become partially negative. And because this is partially negative, this is more electronegative than carbon. Partially negative. So since this is more partially negative than carbon, okay, so the dipole between carbon and bromine will go to bromine, and this carbon here will become partially positive. And to disperse the partial positive charge developing here, what happens is that the adjacent oxygen here, no, can share its electrons paingon din here to form like a cyclic bond here. And so you will have a partial bond breaking process here. So in carbon bromine and bromine Ag here, you get a partial bromine Ag bond. Okay, so its intermediate step will be here like this one. You will have a partial formation of bond between oxygen and carbon. The partial bond breaking process you have here, that. And the partial AGBR bond formation here. Okay, and so once you have that one, you will actually get a bond CO bond here. once AgBr is formed, it will carry with it its electron density. Okay, so in this case, now whenever you are introduced with a new reagent, you just have to remember which one is partially negative, which one is partially positive. Okay, so once you have that identified, you can also attack this one. Can also think that can attack this AG can attack this one, can probably form a bond, but the likelihood that AG will form a bond here is very less than here because the electrons from bromine is more available than the electrons diri from oxygen. What happened here in the bond formation process when oxygen here adjacent to this carbon, napilitan siya, no? Because you already developed here. Okay, so what happens again is, okay, you have there positive. The only way that oxygen shared diri because napilitan siya na this adjacent carbon already is partially positive, and since it's possible for it to form a bond adjacent, so napugos siya to form a bond here, which is uh, three-membered ring here. You get your Ag. So once the AgBr is formed, no, it will carry with it its electrons gikan aning a bond, and once it carries with its electron nga bond, you will form a bond here. So once AgBr is formed, Br will pull the electrons gikan kang carbon, and carbon will be depleted with oxygens. It becomes partially positive charge. Okay, this should be partially positive charge here. This 5 minus 4 minutes, you have a partial positive charge developed here, and oxygen will be forced to form a bond like this one. Okay, so here the carbon developed positive charge is dispersed by the formation of bond here, and once the AgBr is fully formed, no, you get your COO. Okay, kuha na siya bond, get your 4 bonds of carbon. So once you get your lactone here, your agent is water. You have to remember that your agent is water. Okay, H2O. So the water will attack which center will it will attack. So you will have to analyze in this 3 center here as man ang partially positive atom. There are two possibilities na partially positive atom. You have your partially positive carbon here. Okay. Partially positive carbon here. Okay. And you have your partially positive carbon kanipod. Yan ang partially positive man, silingan siya kang oxygen which is partially negative. That's how you identify. No? So, asa man siya mo pili? Kaninga carbon or kaninga carbon? So, this will act as a nucleophile, which is electron rich, no? It will donate its electron. It will seek a positive center. You always have to remember that. And what happens? So what happens is that asa siya mo pili kaning carbon or kaning isa ka partially positive carbon here. Piliun kani siya, the carbon is a way to disperse its charge, no? How? Here you have, here this carbon here is much more stable. This is a planar one compared here. This one is more strained. So this one is actually more reactive than this carbon. This one is planar. It utilizes sp2 hybrid orbitals, and this one is the carbon that is more strained. This one is more reactive. So it will attack this carbon here. Okay. And what happens is that you have your lactone here, no, on this side. You have to remember this one is kani plain man siya, no? If this is CH3 hydrogen, this is on the same plane here. What happens is that they are kani COH is on the opposite side of this. Okay, so it will attack this one. What happens is that you form an O carbon OH2 bond. And there is a partial bond formation. This is our intermediate. Kani siya kaning broken line. So there, once you form a partial bond, carbon-oxygen, there is a partial bond breaking process here. Okay, so what happens is that, of course, oxygen will be partially positive here because it forms 3 bonds, and so water will eliminate that. Water will eliminate the hydrogen here to form your OH. So once the OH, once here is the proton is being abstracted, you have your bond here. You actually have your OH, this one bond, OH2. Before this formation, you still get your this and OH2, no? Fully bond formation. You actually get this one first. Okay na lang. But you will have your OH2. Get your 2 here. And you have a positive charge here. So here, what's you will have your water to abstract this. Once the O carbon is fully formed, then the carbon oxygen bond is being broken. Okay. And there should be an arrow here. Arrow. Anyway, it should be an arrow here. Okay, you have your oxygen carbon being broken when carbon oxygen is being formed here. And this is positively charged. And once you get your water, then electrons in it to abstract the proton here. It's positive, and you have your hydrogen. Okay, so we will use the electrons. You can come water to attack your hydrogen. Once you have that, the electrons, we can din add to oxygen, and you will get your OH here. Okay, so kailangan siya nga step. Okay, so generally you have in there, what happens is that because your kani are on the same side, no, wala siya napulihan. So when your OH is, when your OH attack, here in this case, kani, okay, so there is siyang side and you will get your HOH here. Okay, there is a retention of configuration. When you determine the stereochemistry of this one, this is an S. So you have your hydrogen already oriented away from you. This is the first priority. Second, this is an S. Okay, so 1, 2, 3. You have an S. So once you form this one, kani, once you attack, they are on that side na already. This one is a ring. No? Can you imagine? Kani is on the plane of paper. Imagine ni siyang si carbons in the plane of the paper, and CH3 is oriented towards you sa paper or sa inyong phone, and hydrogen is oriented away from you. So when it attacks here, there is siyang side. It wouldn't attack gikan dito nga side. Okay? Or during a side, no, it wouldn't attack here because there is an oxygen here. No, there is a repulsion if it attacks from this side. So it will attack din ang side. So what happened is that this will be pushed paingon dito, but still on the same CH3. will still be oriented towards you, okay? And hydrogen is oriented away from you, and you get your OH on the plane. So when it attacks, it's still on the plane, diriya. So kani plane, plane, you get your plane, plane, plane here. Plane, plane, because this is oriented towards you, away from you, the OH will attack here. And you get the retention of configuration. And that is the purpose of your AG here, to have your retention of configuration here. So it follows substitution reaction, but very not similar to the SN2 reaction. Okay, now let's go to the okay. Did this answer the question? Next one is what's the question? 6.5. The phenomenon of configuration inversion is covered in basing your answers on the preceding from which reaction are likely to take place with overall inversion of configuration. Nangutana pa kaani kinsa man to nangutana? Almeda? Ikaw to nangutana Almeda, ayan?
Yes, ma'am. Ang concept ra sa neighboring participation group akong confused na to, ma'am.
Sa neighboring. So, okay na to. Okay na, Tani.
Yes, ma'am. Ako naman
Okay.
ang concept.
Okay, and this is your neighboring participation. Now, this is adjacent to your positive carbon. Okay, partial positive carbon. It will help to disperse the positive charge here by forming a bond. Like here, you have a ring being formed actually. It's being forced, no? When normally, pag dili na siya, for example, CH3, no, dili siya mag ring participate because there is no available electrons to form a bond. But since you're adjacent to an atom with available electrons, no? So this is negatively charged man. If it is, for example, let's see, for example, here, kulangan og bond si oxygen. Okay? So it's negatively charged. Kulangan og bond si oxygen because we have to remember si mag-start. Kani. Yeah, we'll start here. This one. Basta kabalo na mo nganong negative ni siya when we have already started like carboxylic acid, it should be hydrogen here, right? But since the carboxylic acid in solution dissociates to form so let's say you have your CH3 COOH, okay? In solution plus water, they will dissociate. Okay na mo? It will dissociate to form your CH3COO minus, okay? And so you notice here that oxygen lacks a bond, okay? And the carbon here should disperse the electron, the developed negative charge here by electron delocalization. In some instance, this one will form the double bond, can you see oxygen here? And the negative charge will be in this oxygen. At some instance, you have here. So there is an electron delocalization brought by the double bond here and available electrons here, okay? And so here, that is the driving force here. We'll also try to stabilize. There's two systems that needs to be stabilized. This negative charge here and the developed positive charge. So nakasilingan man siya positive charge, maka-form na siya og bond diriya. And this is what you call as a neighboring atom participation. If it is another atom, for instance, let's say Cl, no, and you have another Cl, the maximum valency of Cl is only one. I mean bond, no, to have its zero formal charge. So when it forms a bond, for example, this is a Cl, when it forms a bond here, Cl will be passively charged. It's more strained, so it's not possible. And here, it so happened that oxygen is negatively charged and it is possible for it to form a bond here. And you notice here that once it forms a bond, the negative charge here is already dispersed and the the charge rates of carbon is also answered. Dispersal of charge on carbon is also answered. So we eliminate the charged oxygen here to form a bond here, a ring, and you also eliminate this one here. But the more charge is being eliminated is the oxygen, carbon. But you have here partial positive. So in any mechanism, whenever you're asked any mechanism, the first step is always to identify which possible atom